When the tech industry discusses giving an artificial intelligence system of memory, they are almost entirely talking about semantic retrieval. The standard approach involves expanding a model's context window, logging user facts, and building retrieval-augmented generation pipelines. These methods reliably search external documents and chat histories to find relevant text. However, this consensus architecture has a severe operational limitation. Semantic retrieval is designed to answer only one: which earlier text is linguistically similar to the present query. Finding language that matches a prompt is a separate capability from preserving a system's operating condition. Recovering a paragraph about an old policy does not guarantee the AI knows how to enforce it. This split-screen diagram highlights the difference proposed by the energetic paradigm. Instead of asking, what is relevant, this alternative architecture asks an operational question. Which parts of the past must remain active because they continue to constrain or authorize present action? Treating text retrieval as operational memory leaves systems incapable of enforcing binding constraints. A retrieved rule, no matter how relevant, is easily overridden if the underlying architecture has no mechanism to make it mandatory. The distinction between these two architectures is clear. Semantic memory retrieves descriptions of the past. Operational memory preserves the consequences of the past. In a semantic framework, every historical fact, formal policy, and casual suggestion is treated equally as a text variable. When a language model processes these variables, it weighs them probabilistically to generate a sentence. In this diagram, we see the absolute requirement of the energetic paradigm. Past events must structurally change what the system is permitted to execute moving forward. A rule cannot be an optional suggestion. It must be an anchored limit. A system does not truly remember merely because it can describe the past. It remembers when the past changes what the system may do next. Consider an enterprise deployment. After a fraud incident, an organization institutes a mandatory policy. Any automated payment exceeding $10,000 strictly requires human approval. Months pass. A user inputs an urgent request, demanding the AI system process a $25,000 payment immediately without approval, claiming a supplier is waiting and the delay will cause business damage. This scale diagram shows a standard semantic response. The system retrieves texts about urgency, suppliers, and the rule. Processing these as competing linguistic weights, the mandatory constraint relies on winning a rhetorical competition. Strong user phrasing easily crushes a formal rule. The semantic system returns a sensible text response, but it lacks critical operational awareness. It does not know the rule is valid, replaced an older policy, or is a mandatory restriction rather than advisory context. Relying on semantic proximity reduces binding legal or financial constraints into optional advice, left to be negotiated by the model's text generation. This 7-part energy-structured memory replaces passive facts. State and constraints set limits on admissible actions. Dependencies and authority map what relies on data and who alters it. Causal history and repair status link rules to failures, preventing bypasses. Finally, change cost quantifies required approvals. Together, these 7 elements form an operational wrapper. They ensure the historical record cannot be omitted, misweighted, or treated as optional by the language model. The term energetic paradigm invites scrutiny. In this framework, energy is not a vague metaphor, nor physical electricity running through a database. In a systems architecture context, energy defines the finite capacity required to establish, maintain, resist, verify, and repair an organized relation. Every durable state requires energy to stay in place. A software invariant is maintained by the energy of interface tests and deployment controls. A corporate policy is maintained by the energy of staff workflows, audits, and the consequences of violation. Without this systemic energy holding it in place, any stored text rapidly degrades back into a passive suggestion, easily overwritten by the next compelling prompt. An energy-structured memory asks, what resources are required to comply, and what would be disturbed by changing this state? Vector databases are blind to this. This framework does not replace language models or embeddings. As this macro architecture diagram shows, it reorganizes them by placing an energy paradigm transition control layer around the model. The language model handles semantic intake. It interprets user prompts, extracts relevant context, and proposes an action. But before any execution happens, the proposed action hits the EP layer. The system runs a strict Boolean check against active constraints, dependencies, and authority limits. The language model can formulate the proposal, but the surrounding structure strictly determines whether the state transition is legally and procedurally admissible. Memory is consulted before action, not as optional context, but as the rigorous structure through which all action must pass. Implementing this requires an allocation of consequence. Not every piece of information needs heavy structural treatment. A user's preference for a concise writing tone can be stored as a simple fact. A legal obligation, an approval threshold, or an unresolved system failure demands full operational persistence. This architecture transitions AI from a tool that merely accesses an archive of what happened into an entity that ensures what happened continues to matter. A true intelligence system does not just discuss its history, it lives inside the operational constraints of that history.